right, it's time. So let's get started. And first, let me say hello to everyone. So people here in the room in Toulouse, people at other hubs, people online, or people watching the replays later. Thank you all for being here. So I'm Frédérique Marion. I'm a scientist at the lab, which is a high energy physics institute in Nancy, in France. And it's my pleasure to be giving this talk about CBC science today. So CBC science can mean several things. So first we'll start with the science of CBCs, and then later on we'll move on to discuss the science that we do with CBCs. So first let's start with the CBCs themselves. So CBC stands for compact binary coalescences, and they refer to the final moments of binary systems before they merge. So binary systems of compact objects, so either neutron stars or stellar mass black holes. So in both cases, they are the remnants of massive stars. And they're in a binary system that loses energy through the emission of gravitational waves, and that drives the system towards smaller and smaller orbits until the two objects finally collide and merge. And these events are very rare, and the signal is very elusive, but at the same time, what makes them easier to detect, although you'll hear from Tito that it's not that easy, is that they have a very specific signal. As the orbits become smaller and smaller, the frequency and the amplitude of the emitted signal grows with time until the objects merge. And that makes for a very specific chirp pattern that you can easily identify in a time versus a frequency plot as shown here for the discovery event. And one thing to keep in mind is that the characteristic frequency of the gravitational wave signal decreases with the mass of the system. And the ground-based detectors, such as LIGO or Virgo, they operate at frequencies around 100 Hertz, and that makes them capable of detecting binary black hole CBCs for stellar mass black holes. But of course, we're also very interested in CBCs that involve supermassive black holes. But in order to detect those, then you need to operate at much lower frequencies. And this is what John will be talking about tomorrow. All right, so let's start by looking at the basic characteristics of the gravitational wave signal emitted by those CBCs. And let's start by the emission pattern. So if the inclination of the binary system is such that you are viewing it from a direction that is perpendicular to the orbital plane, then you see the two compact objects run in circles. And the gravitational wave signal also has a circular polarization. So that means that both polarizations contribute equally, and this is maximum emission. If instead you are seeing the system from inside the orbital plane, so you have a side view, then you see the compact objects moving on a straight line. And in that case, the gravitational wave signal has a linear polarization. So you only have one polarization contributing, and you're getting half of the maximum signal compared to seeing the system face on. Then, in terms of a frequency, the dominant frequency of the gravitational wave signal is twice the orbital frequency of the system. And as the orbits shrink, this goes up until the system reaches the last stable orbit, beyond which the two objects will plunge towards each other and eventually merge. And the frequency for that last stable orbit decreases with the total mass of the system. It's about 1500 hertz for a light system with a total mass of 3 solar masses. Think a binary neutron star system, for instance, but then decreases with the total mass and is shifted toward the lower frequencies. But so mass is not the only thing that shifts frequencies towards the lower values. Also, the fact that the universe is expanding is also shifting the gravitational wave signal towards lower frequencies, which means that in practice, the total mass here in that relationship is replaced by a mass corrected by a redshift term, here 1 plus z, z being the redshift. And we refer to this m times 1 plus z as the redshifted mass, the apparent mass, or the mass in the detector frame. These CBC events, they appear in our detectors as transient signals. They last for the time it takes them to enter the frequency band where the detectors are sensitive, and then sweeping up to this maximum frequency that is mass dependent. So that makes for signals that are more or less short. So they can be very short, a fraction of a second, and only a few cycles for the heavy binary black hole systems. They can be a few seconds long for lighter black hole system, or last even minutes for the lightest systems like binary neutron stars. And you have a few examples here in the time domain for various events with different parameters. Then if you look at the signal in the frequency domain, then there is something that is slightly counterintuitive that I want to highlight, which is the fact that although the amplitude of the signal, so the strain radiated from the in-spiral increases with time until merger, the system actually spends many more cycles at low frequencies compared to the high frequencies. So that's because this chirp pattern here becomes steeper and steeper, and is actually not very steep in the early part of the signal. And that makes for a spectral amplitude of the signal that is actually a decreasing function of a frequency. It's a little bit steeper than 1/f. So these are the color traces that you see here are examples. So for various events with the maximum frequency that depends on the mass again. And so the spectral amplitude for the signal are compared in this plot to the sensitivity curve of the LIGO detectors. And comparing the two is what is going to give you the signal to noise ratio. So more specifically, if you square the spectral amplitude of the signal and you divide it by the power spectral density of the noise, so that the square of the sensitivity curve, and then you integrate across frequency, this is going to give you the square of the signal to noise ratio, which is a quantity that we always refer to. Okay, so then the details of the signal are going to depend on the parameters of the system. Let's start by looking at the extrinsic parameters. So things like the direction of the source on the sky or its distance. So these extrinsic parameters are going to impact primarily the way that the signal appears in our detectors and the way that it couples to our detectors. For instance, the coupling to the detector and the detector response is going to depend on the source direction and the polarization, with maximum coupling for directions perpendicular to the plane of the detectors and a more complex response pattern for other directions. Then distance is important, as the amplitude of the gravitational wave decreases with the distance between source and detector. But you remember for what we discussed earlier, distance is not the only thing that is going to affect the strength of the signal for a given mass. Also, the inclination of the binary is going to change that. So we have a degeneracy here, and that's why when we try to measure distance, we typically have a correlation between distance and inclination, because it's hard to tell a distant source with optimal orientation from a closer source, but with a less optimal orientation. And then the direction of the source compared to the detectors is also going to impact the time of flight of the signal between one detector and another. And it's also going to impact the relative amplitude and phase in different detectors. And this is the information that we can use to localize the sources on the sky. And you'll hear more about parameter estimation from Charlie tomorrow. So now let's discuss the intrinsic parameters that drive the dynamics of the system. So focusing on the long in-spiral part, so before the objects merge. So this is an adiabatic process that can be well described or modeled with a post-Newtonian expansion expressed in terms of powers of V over C squared. And when you look at that expansion, then there's one parameter that enters at leading order, and that's a combination of the individual object masses that we call the chirp mass. And that's really the parameter that drives the dynamic of the binary at leading order, and that will be best measured. And then it's only at higher orders in the expansion that enter the mass ratio and also the spin parameters. So that means that although the chirp mass will typically be well measured, if you look at the individual masses, then they're less well measured and their measurements are correlated. And also there are correlations in the measurements of the mass ratio and the spin parameters. And another thing to note is that for the higher mass systems, then the merger and rig down part that come after the in-spiral, they typically represent a significant part of the signal, and sometimes even the entirety of the signal. And the dynamics of those parts is more driven by the total mass of the system. And in that case, you can see, so in the M1, M2 contour plots, you see that those banana-shaped correlation, they tend to become more straight, like in the example of the 2015 event, as this is driven by the total mass. All right, so this was really a description of the very basic characteristics of the signal, but there can be more structure in the signal in some cases. So let's take a quick look at what those extra features can be. So one extra feature is higher order modes. So in general, the gravitational wave signal can be expressed as a combination of spherical harmonics, and the quadrupolar mode is the dominant mode with a frequency of twice the orbital frequency. But there are higher order modes here that have more complex emission pattern in space and have frequencies higher than twice the orbital frequency, and they are usually really pretty much subdominant compared to the main mode. But in some cases, they can become significant, typically in systems where the masses are quite asymmetric, and also for systems that are seen from the edge on. Another interesting feature is the precession of the orbital plane, and that happens when the individual objects have significant spin that is not aligned with the orbital momentum. So that when they have a significant component in the orbital plane itself, and that makes the orbital axis precess, and that changes the inclination of the system compared to the detector over time. And that modulates the amplitude and the phase of the signal. And if you're seeing the system face on, and those modulations are going to be very subtle and hard to detect. But if you are seeing the system from the edge on, then they can become quite spectacular, as in this example waveform here, which is a bit like an extreme case. And then there can be more. So an important part is the post-merger signal, and we'll come back to that later. There can be matter effects when we are dealing with neutron stars and not black holes. We'll come back to that later as well. And then there can be other questions like, is the orbit eccentric instead of just being circular? Or one thing that could happen as well would be for the gravitational wave signal to have experienced gravitational lensing itself on its propagation between the source and the detector. That's not something that we have seen yet, but it could happen. All right, so now let's move on to the science that we can do with the CBCs. So we have detected quite a number of them now with LIGO and Virgo. There are more than 200 of them that have been released in the catalogs that Agatha mentioned yesterday. And if you also include the candidates that were identified in the real-time analysis that we do in low latency, and there are almost 400 of them. So, you know, that's not high statistics, but that's a decent number, and it's there is a lot of science that we can do with that. So let's take a small tour. And let's start with astrophysics. So the plot that you have here on the left, that shows how the events that we had detected until 2020, they were distributed in the masses of the heavier object and of the lighter object. And so the detected sample was dominated by binary black holes. There were a couple of binary neutron stars, a few neutron star black hole systems, as well as a few ambiguous systems where one of the objects we are not quite sure whether it's a heavy neutron star or a light black hole. And so in 2026, we have many more detections, but the overall picture hasn't really changed. And then from the sample that we detect, we try to answer a number of questions. So for instance, what is the rate at which those CBCs happen in the universe? And you want to measure that per type for the BNS, for the NSBH, for the BBH. And you also want to look at if and how this rate evolves with redshift, so evolves with the cosmic time. Then we are very interested in inferring what the mass distribution is for those compact objects in those merging binaries. So what is the distribution overall, but also more specific questions like what is the maximum mass for a neutron star? What is the minimum mass for a black hole? Is there a continuum between these two, or is there a gap between them? Or what is the spin distributions for those neutron stars and black holes. And here, so we need to go from the population we observe to the true population in the universe. And so we need to account for selection effects, account for the fact that some sources, depending on their parameters, are much easier to detect than some others. And you also need to go from the inferred parameters for individual events to inferring the parameters of the distribution. And that's where you need hierarchical inference that Vasco is going to give a lecture on tomorrow. And then with these things, we can try to learn things about, you know, the stars themselves that left those compact objects behind, and also how the binary systems were formed in the first place. And here there are two main scenarios. So either the binary was existing before the black holes, let's say, and there was a binary of two stars, and each of them went supernova and left a black hole behind, and we ended up with a BBH system. Or the black holes were formed first, and then they met each other in a dense environment and could form a bound system later on. So that's the dynamical formation channel. And there is no really quantitative, firm quantitative prediction over which should dominate the other. The expectation is that the first channel of isolated binaries probably dominate, but there's no reason why the dynamical formation channel couldn't also contribute. So let's look at what we have learned based on the results from the latest published catalog, so GWTC4. And for example, let's take a look at the distribution of the mass for the heavier black holes in the binary black hole CBCs that we have detected so far. So that this distribution here, so the function of M1, the mass of the primary. There are several things that you can note about this distribution. So just to explain a bit more what's on the plot. So the blue and the red curves and bands, they are the results from the GWTC4 catalog based on various assumptions for the model describing the distribution. And the dotted black line refer to the previous results from O3. Probably the first comment that we can make is that this is a complex distribution. It's not just a very smooth power law. There are some features there. You need at least two power laws, and also you need peaks to account for some local overdensities. And we have, for instance, an overdensity for masses around 35 solar masses. And this one is very familiar because we have another density at those masses in our detected sample. But this is mainly due to a selection, or partly due to a selection effect. Once you correct for the selection effects, actually the overall maximum in the distribution is for black holes around 10 solar masses. And then another interesting feature or non-feature in that distribution is that you don't have a sharp cutoff at high mass. There are less and less black holes as you go to higher masses, but there's no sharp cutoff. And that's a bit surprising because for the very heavy stars, the expectation is that the supernova should be so catastrophic that the star is entirely disrupted and doesn't leave anything behind. So if we do have black holes around 70 or 80 solar masses, where are these coming from? And this points to the possibility that they are themselves the product of earlier mergers. So that's what we refer to as hierarchical mergers. And we do have a couple of very high mass BBH CBCs that show that this has to be a real possibility, because we don't really know how we can form so heavy black holes from stars in the first place. So this was looking at masses. Now, if we look at the spins, so spins are more difficult to measure, but they're also very interesting. And you have two plots here. So the one on the left is the distribution for the black hole spin magnitude. So that goes between 0 and 1 because it's expressed as the fraction of the maximum spin amplitude allowed by GR. And you see that this distribution, tends to prefer low spin magnitudes, but also has, tails at higher spin values. And here on the right, you have a distribution for what we call the effective spin, which is a combination of the two spin projections onto the orbital axis. It's mass weighted. And here, this distribution is also very interesting because you see that it's quite asymmetric. It's skewed towards positive values, which is kind of what you expect for the formation channels through isolated binaries, because here you expect the spin of the two objects to be aligned with the orbital momentum, which will give positive effective spin values. But you see that the distribution also has a significant fraction of binaries with negative effective spins. And that's really hard to explain in the isolated binary formation scenario, but much easier to explain in the dynamical formation scenario where the spin orientation can be anything when the black holes capture each other and become bound. And we have a couple of specific remarkable events that go also in that direction. So these are two events that were detected in the fall of 2024, and they are quite exceptional in the sense that both primaries in those systems have a high spin that are relatively well measured. And in one case, the spin is also anti-aligned with respect to the orbital momentum. And so that points to cases where it's tempting to interpret this as the primaries being the product of previous mergers, and then you have first a merger, and then you need to to form another binary system, which also points to the dynamical formation. So we have results that, still speaking qualitatively, tend to agree with the notion that probably the isolated binary formation scenario dominates, but with identified contributions that are more likely to come from a dynamical formation. All right, so let's leave black holes for a while and turn to neutron stars, as CBCs with neutron stars are very rare. We only have a few of them, but they're quite unique and very special. And as an example, I can remind you, you've probably heard this before, but remind you of all the results that we could have with the 2017 binary neutron star. So that was the first one we detected. It was a strong signal with a signal-to-noise ratio of 32. It was also one of the first events that were well localized, because they were localized with 3 detectors and not just 2. And this one was absolutely unique in the sense that there were counterparts identified across the whole electromagnetic spectrum. So a short gamma ray burst and the afterglow of the GRB, and then a kilonova. And that event then showed, confirmed the suspected connection between BNS CBCs and short gamma ray bursts. The gamma ray burst and the gravitational wave signal came within less than 2 seconds of each other. And that showed to high precision that gravitational waves and light do travel at the same speed indeed, as predicted by GR. This was also the first confirmed observation of a kilonova. So the light from the kilonova is emitted by the hot ejected matter in the merger process. And this was confirmed as a production site for some of the heaviest elements that we find in the universe. And then it was also a tool to study the extreme matter neutron stars and to measure the Hubble constant. And we're going to go into more details about this. So first, let's discuss this investigating extreme matter. So the neutron stars, they are really super dense objects. A spoonful would weigh 1 billion tons. So that's really high density, even much higher density than the density in atomic nuclei. And the bottom line is that this is a state of matter that is unknown, and we don't know how matter behaves in neutron stars. And it's not easy to investigate, obviously, but gravitational waves do give us a tool to investigate. And one way to do that is to try and measure the subtle matter effects in the waveform emitted by the BNS CBCs. And that happens because as you get closer to the end of the inspiral, then the point particle approximation breaks down. And if you have neutron stars, the system does not behave in the same way as if you had two black holes. And that's because each neutron star starts to be deformed and have a tidal deformation because of the gravitational field of the companion. And that affects the dynamics of the system ever so slightly and can leave the measurable imprint above a few hundred hertz. And so that's not something that we have really managed to measure with the 2017 event. We could only place upper limit on the deformability of each of the two neutron stars. So we couldn't absolutely measure a non-zero deformability, but that already tells you that the neutron stars are likely more compact rather than less compact, because if they were less compact, then they would be more deformable, and those effects would be larger and would be measurable. And those upper limits allowed to constrain what the radii of the neutron stars are, and learn a little bit on the equation of state and disfavor the equation of state that would lead to less compact stars. And moving on to cosmology, where CBCs are new and very interesting tools for cosmology, in that they allow to measure the expansion of the universe, the famous Hubble constant H0, in a different way. So to measure H0, you need to relate the distance, the distance of a source to its recession velocity. And the beauty of the CBCs is that they provide a direct measurement of the luminosity distance. So that provides one key ingredient. Then you need the other one, which is the recession velocity, which is typically provided by redshift. But the gravitational wave signal does not give you the redshift. That's because we only measure the apparent mass, which is a redshifted mass, and you have a full degeneracy between the mass at the source and the redshift. So you need to get the redshift in other ways. So if you're lucky, then an electromagnetic counterpart can give you the redshift right away, like that happened with the 2017 BNS, but that's what we call the bright sirens, but they're rare. But then if you don't have an electromagnetic counterpart, as happens with the many BBH CBCs that we detect, there's still information that you can use. So one approach is to use the redshift of all the galaxies that you know are out there in this localization box that you can estimate for your source. So you're including many galaxies, only one of them at best is the right one. So you're adding measurement noise, but with statistics, you expect that this is going to converge to the right value. And this is what we call dark sirens. And there's another thing that you can use that is actually quite powerful. So it's not as straightforward, but let me try to explain anyway how we can use the information about the mass distribution of black holes to do this kind of measurement. So imagine for a second that all black holes had the same mass, and you knew that mass to be 10 solar masses. Then from the apparent mass you measure in the detector frame, you would be able to know immediately what the redshift was that brought these 10 solar masses to the value that you measure. Of course, the black holes don't have all a mass of 10 solar masses, but they do have a mass distribution. And this mass distribution at the various redshifts gets projected onto your detected mass distribution with various shifts. And then you can find the Hubble constant value that allows you to unfold that projected distribution in a way that you get the same mass distribution at all redshifts. So this is complicated by the fact that you don't know the mass distribution a priori, so you have to infer the mass distribution parameters and the Hubble constant value at the same time, but this turns out to be quite a powerful method. So let's look at the constraints that we are getting these days. So based on GWTC4, so this shows the posterior distribution for H node obtained with several methods. And the narrower this distribution is, the more constraining your method is. So the yellow curve is the one from bright sirens. Well, actually, it's a sample of one. That's just the 2017 BNS. So that's very direct and powerful, but very low statistics. And then the spectral sirens, so based on the mass distribution, is the red curve. And when you, on top of that, you add the dark sirens with the galaxy catalog, you get the blue curve. So just a little bit more information. And when you combine everything, you get the black curve. So that's our best constraint today. And you can compare it to the magenta band and the green band that are the measurements done with the traditional H0 measurements and that don't agree with each other. So you see that we are still far off from being able to weigh in that disagreement, but that's the ultimate motivation for doing this kind of measurement to weigh in the Hubble tension issue. All right, so in the remaining minutes, I want to turn to the last topic, which is probing extreme gravity and testing general relativity with CBCs. And just to highlight how those systems are unique to test a GR. I have included a plot here that shows those BBH CBCs in a 2D plot that shows the space-time curvature involved and a typical time scale involved. And you see this is orders of magnitude off from what happens in the binary pulsars or in the solar system in both dimensions. And another way to look at that is to look at for instance, the speed of the planets in the solar system. They are at the level of 10 to the -5 of the speed of light. If you're looking at the most relativistic binary pulsar, then it's almost 3 orders of magnitude compared to the speed of light. But when you have those binary black hole coalescing right before merger, they reach speeds that are really comparable to the speed of light. So here we are in a regime where we have, extreme curvature, highly dynamic systems, and we can test a GR in that way. And when we are lucky to get strong signals, then we're able to do those tests with some precision. And so the questions that we want to look at here are, first class of questions is, are the gravitational wave properties the properties that you expect in terms of, propagation speed, and also do all the frequencies propagate at the same speed, or is there evidence for dispersion? What about the polarizations? Are there only the 2 polarization states that GR predicts, or are there extra polarization states? And then you can also look at the gravitational wave emission itself and the dynamics of the binary system. And you can ask the question whether when you subtract from the data the GR predicted signal, Is the residual consistent with detector noise, as you would expect if a GR is correct? You can look at whether, if the signal before merger and the signal right at merger and after merger are consistent with each other, or look for specific distortions in the signal. And then there's a very interesting class of questions about the properties of the black holes themselves. So the GR states that the black holes are extremely simple objects that can be described only with a couple of parameters, so mass and spin for those astrophysical black holes. So are the black holes that we are seeing behaving in a way that is consistent with that? So let's take one example from here and one example from there. So let's start with the residual test of the waveform of the binary. So here, the question you're asking is, once I've subtracted my GR signal, is there some remaining signal, or is it just noise? So this is essentially a detection problem. So we're going to frame it in a way that is very similar to detection, as you'll hear from Tito later on. So the question will be, what is the signal to noise ratio in the residual? You have a plot here showing the SNR in the residual versus the SNR of the signal itself. And of course, if GR is correct, you expect the SNR in the residual to be small. But because our noise is not always well behaved, you have to quantify how small you expect small to be. And so for that, for each event, you do some background trials where you also look at the SNR there, and you compare the residual SNR to the SNR in the background trials to look at what the p-value is. So that's the probability of obtaining a higher residual from the background. And then we have a sample of detected events. So we can do that across all our events and check whether we see any evidence for deviation from GR. So if GR is correct, then you would expect this p-value to be uniformly distributed between 0 and 1 across your sample of events. And you can check whether that seems to be the case by looking at what we call the PP plot. So that's probability versus probability. So the fraction of events with p-values lower at a given number, which is the number of on the x-axis. And if GR is correct, then you would expect this distribution that would make for a diagonal curve with some uncertainty, because we have a finite number of events and we have a finite number of background trials. But overall, you see that the distribution is consistent with no deviation from GR. And finally, I want to mention an exceptional BBH event that was detected in early 2025, so almost 10 years after the discovery event. And it was remarkable in the sense that it was very similar to the discovery event. That's the more recent event. So similar signals, similar source properties. But what has changed in 10 years is the detectors, which means that the more recent event was detected with a much, much higher signal to noise ratio compared to the discovery event. And that high SNR allowed to make, some fine tests of the system. So one aspect was what we call the spectroscopy of the remnant black hole. So the black hole that is left after the merger. So it's created in an excited state and it stabilizes by emitting a coda of gravitational waves. And according to GR, so this signal is what we call quasi-normal mode. So it's a superposition of damped sinusoids. And if the black holes are Kerr black holes, then the frequencies and the decay times of those damped sinusoids will be entirely determined by the mass and spin of the black hole. So if you detect at least two of those quasi-normal modes, and in that case, we detected two very well, and the third one, a little bit, and that allowed to check whether things looked consistent with the remnant black hole being a clear black hole, and it was. And the other very exciting thing is that this event allowed us to test for the first time Hawking's area theorem, that says that the area of the black hole horizon can only grow. And the horizon area is proportional to the square of the mass. So in order to check the theorem, you have to be able to measure independently the mass of the original black holes and the mass of the final black holes. So the original black holes, you measure the masses from the in-spiral phase, and the final black hole mass you measure from this ring down signal. And with this, we were able to show that indeed the area of the remnant black hole was larger than the sum of the areas of the two original black holes. All right, so that's essentially what I wanted to mention today, but since you've had a few lectures by now and you will have many more today and tomorrow, just wanted to map the various lectures to see where we are. So it obviously all starts with detectors. You heard that about that from Viola yesterday. Then you need to properly calibrate and characterize the data of your detectors. And Francesco is going to cover that right after me. You need to release your data and make them public. Agatha covered that yesterday. Then you need to detect those CBC signals, and Tito will explain how we do this just later today. And once you have detected the signals, then you want to infer the properties of the sources. And Charlie is going to cover parameter estimation, so how we do this tomorrow. And then you can do science with those sources. So that's what I covered today. So you see, we discussed kind of the end product before discussing all the steps so that you can see where we are going. But you need all of this to happen before, and also in order to extract the science from samples of events in a statistical way. That's where you need a hierarchical inference, and Vasco's lecture tomorrow. And then you want to do more with those CBCs, and for that we'll need next generation detectors on Earth, and we need to cover other wavelengths, and that's what John is going to discuss tomorrow. And for all of this, you essentially need signal processing everywhere, so that's why you need Quentin's lecture in the very first place. And I'll end with a list of a selection of references. So this is not exhaustive, of course, but I've provided links to papers for the two historic CBCs, let's say, so the Discovery BBH, and then the first BNS, and the recent results that we could obtain from the latest catalog and from a few exceptional events. And in all cases, I've linked to the science summaries that the LIGO-Virgo-Cagra collaboration provides. I think they're really useful. If you don't have time to read a full paper, then the science summary typically is a very good entry point, to get a sense of what science is in the paper. I find them useful myself. And if you allow me, I wanted also to advertise a Scholarpedia article that I wrote with Steve Fairhurst about the science of CBCs. We tried to aim for some intermediate level, between outreach level and expert level. So for this reason, maybe you'll find it useful. And with that, I'll stop.
Thank you very much. We are a little bit late over time, so we will take the questions online. If you have questions, also we can take them, but we try to answer as quickly as possible. So we have a first question by Leandro Fontes Ferreira da Silva, who asks, I always add this question, why the masses are correlated by a banana-shaped plot? His words.
Yeah, so that's because the banana-shaped plot is an isocontour of chirp mass. So that's the shape that keeps the chirp mass constant.
That's the equation is the one with the power.
Yeah, so it's a combination of powers of the masses.
Okay. Thank you. We have another question by Mehdi El Bouadati. In slide 10, can you please describe what the y-axis refers to?
Okay. Describe what?
Slide 10, the y-axis.
Yeah, so the y-axis is the relative abundance of those mergers. So that's the merger rate distribution across the mass of the primary. So that's, yeah, number of mergers per unit volume, per unit time, per unit primary mass.
Okay, thank you. And finally, one last online question by Ada Khan. Regarding spectral sirens, how do you also account for gravitational lensing? How does gravitational lensing affect our understanding of the redshift and black hole masses?
Okay, so first, the main thing is that you have to realize that at least at the stage we're at, gravitational wave lensing of the signals is expected to be very rare. So that depends on the density of lenses that the signal is can cross as it propagates from the source to the detector, and until recently and still today, our detectors, the reach of our detectors is such that we are not probing a very, very large volume of the universe. So the probability of crossing a lens was rather low. Of course, as the detectors become more and more sensitive, that probability is getting higher and higher. But today, it's about at the level of 1 in 1,000 events. And we haven't detected 1,000 events yet. So, by default, you're not really expecting gravitational lensing. But we do search for signatures of that happening anyway.
Yes, thank you. I think there is a paper for that. There are papers at each of the catalogs which explore, is there any lensing?
Yes.
So far, the answer is no.
Yeah, absolutely.
One day, maybe.
We have a couple of lensing papers, and there is one based on the GWCC4 catalog.
Thank you. Any question here in the room? Yes.
It seems to me that you used the wording polarization for two different things. So the first one was about the source orientation or inclination, and then it was the H plus and H cross polarization for coupling with the detector. Am I right?
Yes, but in one of the cases, I should have said polarization angle. So, so one thing is fundamental, which is do those gravitational waves have only two independent polarizations, so just one H plus and H cross and nothing else, and then you have this so the circular binary appears like an ellipse, depending, and this ellipse has some axes that kind of define the polarization of that particular system, and then how those axes how rotated compared to the axis of your detector. So that defines the polarization angle and affects how the signals are going to couple to your detector. But
is this the same as the inclination, or is it different?
So it's different from the inclination. It's an
Different.
extra parameter. So, you know, the inclination is going to define how much your circle becomes an ellipse, let's say. And then the polarization angle is how the axes of the ellipse are with respect to your detector.
Okay. Thank you very much. Thank you again, Frédérique.
Sure.